Okay. Welcome you all to the discussions of the fourth concept in proton NMR spectroscopy. As we discussed before, when you consider analysis of a proton NMR, when you're trying to assign the structure of a given compound using your proton NMR spectrum, you have to consider four things, right? We talked about the number of signals, the position of signals, which is in turn called chemical shift, and the intensity of the signals, which is given by the integrations. And today we'll be talking about spin splitting of signals. What do we mean by this spin splitting signals? This is what we mean by. Some of them are split more than others. For example, this is split 3 ways. This is split 5 ways. So this is much more complex. Splitting pattern. This is a doublet, right? So there are some terminology, there are some patterns to learn about and to find the reasons why we see these peaks as split, right? So that's what is going to be the discussion of this particular lecture. For example, if you were to find out different types of hydrogens that this compound has and predict the number of peaks accordingly, you would say there are 3 different types, because these metals are all chemically equivalent, so that produces 1 peak. This hydrogen is different than this hydrogen because this is housed on this carbon, whereas this is housed on a carbon which in turn accommodates 2 bromines, right? In other words, this is attached to a carbon that only has 1 bromine. This hydrogen is attached to carbon which has 2 bromines. So the chemical shift of this is different than this one. Chemically this is different than this one. So magnetically this is different than this one. And that's the reason why you see 2 different peaks for this. And the chemical shift of this is further low, further downfield than this one. So this is much more shielded than this one. Okay. So the green one is the most de-shielded one, because of the electronegativity of these bromines, right? In other words, this is experiencing more magnetic field than this would experience. Its electron density is drawn away, so the protection that electron cloud offers, the magnetic field that is created by the electronic field, is taken away. So the green hydrogen here experiences a higher magnetic field, and that's the reason why it has a higher chemical shift. In olden days, the field was changed and the radio frequency was the electromagnetic radiation was kept constant as a constant, and so this terminology is kind of paradoxical, counterintuitive to call a higher frequency as a lower field, but anyhow, that's not the case these days. You can call this as higher chemical shifts and this side lower chemical shifts, but remember, this is called high field and this is called down field. This area is shielded, this area is said to be de-shielded. Okay, the peaks that come here, or the hydrogens that resonate in this area, are said to be de-shielded. These hydrogens are said to be shielded. They are attached to electropositive atoms compared to these ones. Okay, so anyhow, that's what we have been discussing so far in proton NMR. What we are going to discuss today is that these signals that you see for this proton and this proton are not quite singlets as you expect. They are rather doublets. They integrate combinedly for 1 proton. This also combinedly integrates for 1 proton, and so is this one. Okay, so it's not that it integrates for 2 protons and this integrates for 2 protons. It's just that the peak is split. Some hydrogens are coming here, some hydrogens are coming here, some hydrogens are coming here, some hydrogens are coming. How is that possible? We only have 1 green hydrogen, and here we have only 1 blue hydrogen, so we should be expecting only 1 peak, right? However, this is because of the local magnetic fields differences. Local magnets, there are tiny magnets. Each spinning nuclei is a magnet. So this is a magnet and this is a magnet, and now we have an external magnetic field, and the external magnetic field is what is causing the spin states, different spin states for this spinning nuclei, but the external magnetic field, the effect of this external magnetic field on this particular magnet is influenced by this magnet in turn, right? So depending upon how the orientation of this blue magnet is compared to the external magnetic field, this hydrogen would experience either more or less than what it would otherwise experience if this blue hydrogen was not to be there. Okay, so let's say we had a compound where even this was a bromine, and then this hydrogen would be a singlet. It would not have this splitting pattern. This is called spin splitting for that reason, and then we'll talk about some of those causes and effects. Okay, and to the extent that this is split, the distance between these two peaks is called coupling constant. The more the influence of for this nuclei on this would give you a bigger coupling constant. That is the extent of coupling. Okay, so on that extent of coupling, or the intensity of the coupling, is dependent on the dihedral angle between these two hydrogens. Okay, how well they could influence each other decides the coupling constant. If this green hydrogen is affected by this blue hydrogen, or the magnetic field of this hydrogen is affected by the magnetic field of this, so should be the other way around. The magnetic field of the effective magnetic field of this hydrogen is affected by the local magnetic field of this hydrogen. Okay, to the same extent. So the coupling constant, the distance between these two peaks, will be same as the distance between these two peaks. So it's reciprocal, right? Okay, so we have been discussing about 4 factors so far, 4 concepts, or 4 different types of phenomena here. The number of peaks, the integration of peaks, the position of peaks, and the pattern of the peaks, the appearance of the peaks. That is spin splitting. Let's go into the details and see what is it causing for this one to be, for this effect. Okay, what is the root cause of this effect in more detail? We just browse through the reasons, but there's much more explanation that I have in a few slides. Okay. So this is the intensity of coupling. As I said, the coupling pattern depends on the dihedral angles, and the coupling constant increases in this way. From here, the coupling constant is 0 here. In other words, both the hydrogens are coming at the same place. The hydrogen or the nuclei is not split, whereas this is starting to split. And as you can see, the external and the outside peaks are growing taller. If you look from here, okay. So that is decided by the dihedral angle. And the number of the splitting, this is a quartet, and some are triplets, some are doublets in other peaks that we saw in the previous spectrum. That's caused by the number of magnetic nuclei that are on the adjacent carbons. Okay, so that's what we are going to learn today. Anyhow, so let's look into the reasons and the orientations that we have been talking about neighboring nuclei. This is the direction of the external magnetic field. Let's imagine that this has the applied field from B and B naught. Okay, and in the absence of any other factors, this nuclei has 2 spin states. Either it's aligning with the magnetic field, and this is the orientation of the local magnetic field that is generated by the spinning nucleus, and as a result, this is at a lower energy state compared to this opposing magnetic field that is generated by the spinning nucleus. This is probably -half, and this is +half of the spin states if it is hydrogen. We are in hydrogen NMR, right? So the energy difference between this is proportional to the magnetic field that we are applying, right? The bigger the magnetic field, the bigger the difference, and the higher the frequency that is required to cause the resonance or the spin flip. Any change in B naught will cause a change in the energy at which the resonance condition will occur for a proton of a given chemical shift. If you change anything that the external magnetic field that this nuclei experiences, that change would result in the change of the delta E, that in turn reflects at the radio frequency that is required to induce the resonance. Let's say the effective magnetic field, this is applied magnetic field, B naught is applied magnetic field, B effective is the effective magnetic field that this nucleus experiences, is different or lower than the applied magnetic field. In that case, you would have a lesser gap between the two spin states. If for some reason something increases this external magnetic field, that would cause that a higher energy difference. The local magnetic fields that are surrounded would be causing those effects. The external magnetic field is constant, mind you. This is the magnet that we have in the NMR room, right? This is a superconducting magnet strength of the magnetic field. So that's constant always. So what would influence the B effective, that is the effective magnetic field? The local magnetic fields either would reinforce the external magnetic field or they would oppose the external magnetic field. As a result, the energy levels are further split tiny by tiny amounts. Okay, so instead of one degenerate level, we have a couple of couple of levels which are little different from one another. Okay, anyhow, let me show you what I mean by that. So we don't have any nuclei here, right? Let's take a case where this hydrogen has a carbon, this carbon has a neighboring carbon that in turn has a hydrogen, and we are looking at neighboring hydrogens, neighboring nuclei. We are not taking into consideration the field of this carbon. We are only looking at the hydrogens in hydrogen NMR for the reasons that we already saw. Okay. So the magnetic field of this, or the spin state of this, can align with that of external magnetic field, or that would, if it aligns, then it is reinforcing the external magnetic field. So this nuclei is experiencing not only this amount of magnetic field, but also the magnetic field that is caused by this nuclei. The B effective is greater than B applied magnetic field. Okay, let's say that would cause slightly higher chemical shift for this nuclei. Let's say you have a case where the local magnetic field of this hydrogen is opposing the external magnetic field, and as a result this nuclei experiences lesser effective magnetic field compared to the external magnetic field, and that would cause the energy level difference to go on to the lesser side. Okay, one would cause increase in the delta E, one would cause decrease in the delta E because of the effective magnetic field that this nuclei experiences is different. It's pretty complicated if you don't get it. I'm also trying to simplify it in the process. I'm not sure whether it's confusing you. What I mean to say is NMR is collected average depiction of quite a few data points. It's not derived from one molecule. It's obtained from thousands of millions of these molecules in the sample. And so if you have one neighboring hydrogen, one neighboring nuclei, that can orient in two ways, right? So all the molecules, so let's say 1,000 molecules are there in our sample tube. Those 1,000 molecules have to align or have to oppose. They have only two choices. That's the possible ways that one nuclei can orient, right? If you have more of those and you have more alignments, and that's the reason why the peaks are spread further. So in the previous case, we had a molecule where this hydrogen had a reinforcing alignment of the neighboring nuclei. In this molecule, we have an opposing nuclei. So this molecule would give a shift of higher field, whereas this molecule would have the shift towards lower field. So as a result, the peak is not where it used to be, rather it is symmetrically divided into two peaks. That's why it's called a doublet, because of one nuclei. If we had three neighboring nuclei, these three neighboring nuclei could orient in four ways. Let's say we have 1000 molecules, and there are different ways that each neighboring nuclei can orient itself. In this molecule, all the neighboring nuclei are orienting in the direction of the magnetic field, external magnetic field. So the B effective is increased by these three reinforcing nuclei, right? So the peak is shifted towards downfield, towards higher chemical shift, because of the local magnetic field, induced local magnetic field, right? Let's take another molecule where the case is different, where two of the hydrogens are reinforcing, one of the hydrogen is opposing the external magnetic field. So the net effective magnetic field that these hydrogens are experiencing is still greater than what it would otherwise experience, right? But it's not as much as this is when three nuclei are reinforcing. Only two of them are reinforcing. So this kind of molecule, this orientation would give a peak. There are three different orientations that we can have. Instead of this nuclei opposing, this nuclei could be orienting. So anyways, all three nuclei and two nuclei can orient and one nuclei can oppose, and these are the three possible orientations in three different molecules. In one molecule this hydrogen is opposing, in another molecule this hydrogen is opposing, in a different molecule this hydrogen is opposing. So averagely all these three molecules would give the peak coming like this. Remember that these all the molecules are of the same compound, okay, just that it's a different compound, different molecule, okay. And this is the average data collection, right? This is the FID that collects all the data points, remember. And let's look at other possibility where two nuclei could be opposing, one nuclei is reinforcing. So the net effective magnetic field that this CH2 or this hydrogens feel is reduced to some extent, because there is one nuclei that is opposing in total. These two cancel out each other. So one of the nuclei is opposing the external magnetic field. As a result, this CH2 is experiencing lesser magnetic field of the applied field than the applied field. So as a result, the peak, instead of where it should be, it is slightly shielded. And again, there are different orientations, but the net effect is same. So that's why we have this one peak coming from all these three orientations. So two are opposing, one is reinforcing. Here two are opposing, this one, then one is reinforcing. So all these orientations would give the peak at the same place. And the last orientation that we can think of is that a molecule where all these neighboring nuclei are opposing the external magnetic field. As a result, you get a peak further upfield, because now it is shielded. The external magnetic field has been blocked by this induced magnetic field. So this nuclei is said to be shielded, okay. So that's coming towards a higher field. If you translate all this through the Fourier transformation, you get a peak like this, quartet. So this quartet is originated because of the four orientations that we can think of for the neighboring nuclei. This is the nuclei that is under consideration. That is the nuclei that is responsible for this one, these hydrogens, okay. So these hydrogens are the neighboring hydrogens. Because these have their own induced magnetic fields, they can orient either in the direction of the external magnetic field or opposing to the external magnetic field. As a result, they could reinforce the external magnetic field or oppose the external magnetic field. So the B effective would be either increased in these two orientations or decreased in these two orientations. As a result, instead of one single peak that should have been in the center plane of this one, so the chemical shift is average of this center point of this quartet, okay. This peak is further split in four ways. So some molecules are giving this peak, a few other molecules are giving this peak, and some other molecule is giving this peak, and the other molecule depending upon the orientation. To mind you, all these molecules are of the same compound. We have hundreds and thousands of these molecules in the NMR tube. So we are collecting the data points from each molecule. So depending upon the orientations of the neighboring nuclei, the chemical the shifts would be different, but they are not drastically different. They are slightly. Like they say, this is coming at 2. This might be 2.08, 2.1. This might be 2.1.9, 1.8. So okay. So slightly shifted in both the directions, towards downfield as well as towards high field than the average position where it should have come. Okay, that is what is called coupling. The spins of these nuclei are affecting the spins of these nuclei, the spin levels of these nuclei, and as a result it's called spin-spin splitting, and this results in a quartet instead of one resonance for these hydrogens. Okay, and the intensity is reflective of the orientation. The number of molecules that can be in this state is much higher than in this state or in this state, and so is in this state, right? So that's why these two peaks, these two orientations are more populated, so you get a taller peak than these two peaks. Okay. So this is again another example. This is the same molecule. Now we will consider the effect of these hydrogens, HA and HB. Okay. So we have 3 HBs that are chemically equivalent. So they should have come as a singlet. But because of these two magnets that are in the neighboring on the neighboring carbon, these have their own magnetic fields, and they could orient in the direction of the external magnetic field or in the opposing direction of the external magnetic field. This is in the direction and this is opposing, whereas one is opposing and one is reinforcing here. So the actual signal should have been here, but we get a peak where one is downfield shift, high field, upfield shift, downfield shift, and then one is upfield shift. As a result, you see that it's not a singlet, but it's a triplet. So if you have 2 neighbors, you get 3 peaks. If you have 3 neighbors, you get 4 peaks. So this is kind of a generalization, right? It's becoming a generalization. That's why this is called N+1 rule. N is the number of attached hydrogens, neighboring hydrogens attached to the neighboring carbons. Okay, we're not looking at farther away, we're just looking at the immediate door to this carbon. Okay, and this has 3 hydrogens, they are counted as neighbors. If this has another 3 hydrogens, they would be counted as neighbors, and you just apply that as N and substitute N in the N+1 rule, and that would give you the splitting pattern. Okay, let's take an example here. This is bromoethane. These hydrogens which are colored in red are experiencing 3 local magnetic fields influenced by these 3 local small magnetic fields. These are called induced magnetic fields, and as a result they would be split in 4 ways, and that's why this is a quartet, and it is attached to a bromine, so the chemical shift is much lower compared to the other one, which is for methyl. And this methyl group has only 2 neighboring hydrogens, so N+1 rule tells us that this should be split into 3 ways. That's why it's a triplet. The integration also tells something here. This height is in comparison to this one in 2:3 ratio, so that 2:3 ratio corresponds to 2:1:3 here, right? Remember, the integration is just the ratio. Okay, so to understand the concept of spin-spin splitting, but this spin-spin splitting and this N+1 rule is simple only when you have chemically equivalent neighbors. In other words, where the coupling constant is same as one another. Otherwise you have a complex splitting pattern, which we will see in a minute. But again, let's look at this simple first order coupling here. This is HB having an effect on HA, and that's coupling with HA, and the extent at which it couples is given by the coupling constant. This is called Z is symbol for coupling constant, and the coupling constant is given in the hertz. Okay, though the NMR scale is on ppm, it's given in the hertz because the actual scale of NMR is in megahertz, right? Just that for the convenience sake, to have some references to nullify the effect of the different field strengths, we have invoked something called ppm or chemical shifts, but ppm can be converted back into hertz if you know the field strength, or the other way around, right? So these distances between the peaks of the same hydrogen is called coupling constant. Okay, the coupling constant is proportional to the dihedral angle, and to the extent which the neighboring nuclei couple. Okay, so this hydrogen here has two neighboring nuclei. Because of that, they are oriented in three different ways, so we get three peaks for this hydrogen, and this is called a triplet, and they are in 1 to 2:1 ratio, the intensity of these peaks, and the distance between those peaks is given by the coupling constants. These are chemically equivalent. If they are chemically non-equivalent, then the coupling constant of these, the effect of this would be different than the effect of this on this one. Then you see different type of spreading. Okay, so we'll talk about those in a minute. And this has three neighbors, so this is split into four ways. So this comes as a quartet. Rest of them are not hydrogens. Okay, when you are considering this coupling, you just count the hydrogens that are on the neighboring carbons. Don't count the hydrogens on the same carbon unless they are diastereotopic. Okay, that's the catch. As long as there is no diastereotopic group, as long as they are chemically equivalent, you can ignore them and don't count them as neighboring hydrogens. Okay, so anyhow, here are some examples. You can predict by counting the number of neighboring hydrogens. You can predict the shapes of the respective hydrogens that you are interested in. For example, I'm interested in this CH2. I want to know the shape of this peak. Then I just look at the neighboring carbon and see how many hydrogens are attached. There are two hydrogens here, so this must be a triplet, and so should be this one, isn't it? It has two neighbors. It has two neighbors, plus there are three neighbors on the other side, so I have to look on both sides to count the number of total neighboring nuclei. So this has 5 nuclei neighboring carbons, so it splits in 6 ways. So this gives a sextet, this gives a quintet, this gives a triplet because it has 2 neighbors. So if I know the neighbors, I can predict the shapes, or if I know the shape, I can predict I can calculate the number of neighboring nuclei. So it's one or the other way, one and the. So the n+1 rule gives us the shape of the peak. Okay, this is given by this Pascal triangle, so you don't have to memorize it, but nevertheless the intensity of each peak is given by the Pascal scale. We know that this can be derived by the n+1 rule, but how do they look like? Is a triplet like 1:1:1, or is it 1:2:1 ratio? So that is given by the Pascal's triangle. And this pattern only holds good for those situations when the neighboring protons are equivalent. Why is that? And what happens if the neighboring protons are not equivalent? Equivalent by equivalent we mean chemically equivalent, all right, or at least they are coupling to the same extent. The coupling constants are same, not chemically equivalent. Sorry. So for example, we have a singlet for this methyl because it does not have any neighboring hydrogens, the hydrogens on the neighboring carbon. This is ethyl group, you see a quartet and a triplet. This is propyl group, you see a triplet, a quintet, a sextet and a triplet. The sextet is for this one because of the 5 neighboring hydrogens, 5 neighboring nuclei, right? Okay, so these are the typical patterns. If you see something like this in a given NMR, the purple should strike you. And if you see a quartet and a triplet, depending upon what it is attached to, the chemical shifts would be different, but the shape would be same. So the triplet and the quartet should bring an ethyl to your mind, and this would be a singlet because this CH3 is same as this CH3 is same as this CH3, and they're chemically equivalent. So the chemically equivalent protons do not couple with each other, and they give one singlet. Okay. And what if you have an isopropyl group? What would you expect for this hydrogen? How many neighbors does it have? It has 3 neighbors here, 3 neighbors here, so in total it has 6 neighbors. So this is a septet. And this methyl and this methyl are split in 2 ways because they are chemically equivalent, but there is one hydrogen as a neighbor, so that hydrogen splits them into doublets. So these are typical patterns that you see for some of the groups like isopropyl, tertiary butyl, methyl, ethyl, propyl. So you have to remember some of these things. You don't have to remember, but it should become second nature to you. As soon as you see a quartet and a triplet, an ethyl should come to your mind. Okay, some of the typical patterns that we see are listed here. This is a doublet of a doublet. This is a doublet and this is sorry, it's not a doublet of a doublet. It's just a doublet and a doublet. This is a triplet because of this CH2, and this CH2 is a doublet because of this neighbor. So you see a triplet and a doublet for this kind of a fragment. This is a methylene flanked by another methylene, so each one of them splits the other one in 3 ways. So you expect a triplet and a triplet. And you have a ethyl group situation here again, we already talked about, and you have a doublet and a quartet situation here. This hydrogen is quartet because it has 3 neighbors, and these hydrogens are coming as doublet because they have 1 neighbor. Okay. And the intensity and the chemical shift. The chemical shift would depend on what else is attached to these, and the intensity of this is given by this ratio, the Pascal's triangle that we talked about. Okay. So if you have any questions, please feel free to clarify them with me either in person or through emails, through discussions on my courses. I would be happy to assist with that. So the magnetic influence falls off dramatically with the distance, so we don't see farther away coupling, like we don't count 3 doors away, we only count immediate door hydrogens that are living on the immediate carbon, that are attached to the immediate carbon. Okay, so the effect of this spin splitting decreases with the distance, so we don't couple the bonds that are 4 bonds are away, 3 bonds away, at least in very rare cases where we have restricted rotations. We can see long range couplings, but at your level you don't have to worry about farther away hydrogens. Okay. And as I mentioned, this n+1 rule has its limitations. You cannot apply this rule to all the situations. It can only be applied in certain situations where first order coupling is in place. Okay. When is it applicable? When the compounds have free rotation on the carbon-carbon bonds, you can apply that rule. And where the hydrogens are held in their position relative to one another, they don't drastically differ from in their orientation, you can use that rule. Otherwise you have to be careful. Okay. And as I mentioned, the coupling constant is measured in Hertz. So this is where the singlet should have been had it not been the case for the neighboring nuclei. Okay, had it not been due to the presence of the neighboring nuclei, my signal should have been a singlet, but because this had a neighboring 1 hydrogen nuclei, so this is split in 2 ways, and that's the average chemical shift, and the ratio is 1:1. The distance between this is given by coupling constant. Excuse me. So one adjacent proton splits an NMR signal into doublet, and the intensity of the single and coupling depends on the dihedral angle. The dihedral angles, again, there is something called a Karp's equation. It's again at a higher level to you, so I'm not going to go into the details. So where else this n+1 rule is applicable? Whenever 2 or 3 different sets of adjacent protons are equivalent to each other, though they are chemically different, you can apply this rule. But in this case, these are chemically equivalent, so you can apply this rule. Okay, whenever 2 or 3 different sets of adjacent protons are equivalent to each other, we can use n+1 rule to determine the pattern. So we have 2 plus 2, 4. Because of this 4, this is split in 5 ways, so this is a pentate. And because of this CH2 is a triplet, and so is this triplet, but these two are chemically equivalent, they have the same chemical shift, so they come at the same place. So the integration would be 2 to 4 ratio. That's what is seen here. So this is NMR for this dichloropropane. And you can apply this rule even though this CH is different than the CH2 chemically, but whenever 2 or 3 different sets of adjacent protons are not equivalent to each other, we can only use the n+1 rule to determine the splitting pattern only if the coupling constants are identical. If the coupling constants are not identical, they would not be as simple as they look here. Okay, so this hydrogen is coupling to the CH2, or the magnetic field strength of this is influencing the magnetic field of this to the same extent that these two would influence. So it looks as though it has 3 equivalent neighbors, but they're not chemically equivalent, they're just magnetically seems to be of the same strength and same influence, right? So here the JAB, the coupling constant of A to B, is same as the coupling constant of B to C. In that case, you can total them combinedly and then calculate the number of splitting patterns. So we have 3 neighbors. As a result, this CH2 is a quartet, right? This CH2, and this CH2 splits this singlet in 3 ways. So this is the triplet for this hydrogen, and these CH2s are split in 3 ways, but that has a different chemical shift, different integration. This accounts for 2 protons. The 2 protons is for this one. Okay, so do you understand how to deduce the information from a given splitting pattern? And we'll move on to the next one. So what is the condition here? Of course, there should be a free rotation around the carbon-carbon bonds. And whenever 2 different sets of adjacent protons are not equivalent to each other, we can still use the n+1 rule to determine the splitting pattern only if the coupling constants are identical. It's just like same as the previous slide. Okay, they're chemically different, this CH3 and this CH2, but they couple to the same extent here, so they can be totaled into 5, and then 5 would split this CH2 in 6 ways, so you get a sextet for that CH2, and rest again the same thing. You can vice versa, you can calculate, right? So if the protons are not equivalent, they can have different coupling constants, and the resulting pattern will not be just triplet, but it would be much more complex. It can go into doublet if you have 2 neighbors, or if you have more than 2, then it can be pretty complex. Okay, so we'll see in few slides as to how to decide this kind of complex splitting. So first of all, we need to find out if they are diastereotopic or anisotropic or homotopic. Homotopic groups are related to each other by bond axis, so they don't couple with each other. Anisotropic protons are those which are in the mirror image environments. We already talked about this when we tried to understand as to how many peaks would a given compound would give, right? So I'm not going to go into those things again here. Diastereotopic groups are those which are in different time environments. This diastereotopically related to each other, so they do not couple to the same extent. Sometimes they can result into the complex splitting patterns that we see. Okay, anyhow, here is the case where let's say we have 3 types of hydrogens, A, B and C. The coupling constant between the extent of the coupling that A couples with B is not same as the extent of B coupling C or C coupling to B. So JAB is not equal to JBC. That's the situation we have here. So we have to take into account one at a time. So we cannot combine them as 4 neighbors and predict that the B would come as a quartet, as a pentet. So we have to first take the effect of this into what the CH2 would become. So let's take HA and count them. How many A type we have? We have 2. So as a result of these 2, the singlet of this would become a triplet. So that's the first one. This is called a tree diagram to derive the splitting pattern. Okay, so now each one of them would experience the magnetic field, local magnetic fields and local spin states of these hydrogens. We have two of them, so each one of them would be divided in three ways. So we have a triplet here, a triplet and a triplet, and in certain cases some of them might overlap, in certain cases they may not even overlap at all. So here is a case where they don't overlap at all, and as a result we have what is this, triplet of a triplet. If they are not equal, the JAB is not equal to JBC, and as a result we have a triplet of a triplet. If it were to be equal to the JAB were to equal to be JBC, then we would have had at the max a pentet. The pentet would be much simpler than a triplet of a triplet, right? So that's where you have to be careful when you get into the second order coupling or complex splitting patterns. So this is the case where JAB is equal to JBC, and the coupling constant of A and B is equal to coupling constant of B and C, and as a result these three peaks, the same as this one, we derived first these two would split the peak in three ways. So this and this is same. Up to that point it's same. When does it differ? When JAB is smaller than JBC is smaller than JAB, then they would not overlap. Here JBC is same as JAB, so some of the peaks are overlapping and you would get into a pentet. So this is called simple splitting, this is called complex splitting, or also this is called first order coupling, this is called second order coupling, higher order coupling. Okay, and there can be a situation like this where let's say we are considering the effect of A and C on B. Okay, so let's say this HA is not as HC. The coupling constant between these two is different than these two. Let's say this is a bigger magnet and this is a smaller magnet because of the local environments that these in turn have. Okay, as a result of HA, HB would be split in two ways. That is given by the coupling constant JAB. But JAB is not equal to JBC, so the C would split each one of these in two different ways again, and as a result we get a doublet of a doublet. This is a doublet and we are getting a doublet of a doublet. Okay. Let's say we had two equivalent hydrogens on this carbon. In previous case we only had one hydrogen. In here, let's say the coupling constants of A and B is JAB is different than JBC. So then that would result into complex splitting pattern. So first the HA would split the signal of HB in two ways. So that is JAB. So the signal which should have been a singlet is now split into two ways because of this neighbor. It still has two more neighbors whose coupling constants are different than this one. So these two nuclei would split them in three ways, n+1 rule, right? So n+1 rule can be applied to these two, but you cannot combine this also. Okay, so you have to split the n+1 rule for each set of them and then assign them. So this two nuclei would split in three ways. So you have a triplet. This is called a doublet of a triplet. Triplet of a doublet. Right? This is a doublet and that's converted into a triplet. So this is called a triplet of a doublet. And so let's go back for a minute. You have to first divide the peak or take the one which has a higher chemical shift and then draw this tree diagram. You don't want to do the other way around. Probably that also would give the same thing, but it would be easier for you to derive the tree diagram if you follow this rule. First take the nuclei that is influencing in a much higher coupling constant and then do the splitting and then do the other splitting, that is the smaller coupling constant. So that would give you the tree diagram. Any questions? If not, let's go forward. This is the spectrum of vinyl acetate. This is the vinyl alcohol, and this is acetic acid, and the ester derived from a vinyl alcohol, and acetic acid is called vinyl acetate. And this CH3, this group is a singlet because all the hydrogens are equivalent. They don't couple with each other, and they don't have any neighboring hydrogens. This carbon does not have any hydrogens, so it doesn't get split. Whereas this hydrogen has a neighbor and has another neighbor, so it has two neighbors, but this neighbor is different than this neighbor in the sense this is cis related and this is trans related, so we cannot just do an n+1 rule here. If it were to be n+1 rule, we should just observe a triplet for this, right? But instead of a triplet, we get a doublet of a doublet, as you can see here. And the coupling constants are different, right, to a certain extent, because this is cis relation and this is trans relation. And by looking at the coupling constants, we can say either it's a trans alkene or a cis alkene, but in this case it's not applicable because we have a monosubstituted alkene, so the cis and trans may not be quite valid, but they're not chemically equivalent, not magnetically equivalent. That much you can remember. Okay, and so this proton in turn has two different neighbors. This is not chemically and magnetically equivalent as this one. So this is different than this one because the local field that this experiences is different than the local effects that this experiences. Anything that has a different chemical environment and different magnetic environment would be different on the NMR scale, NMR spectrum. So this would be further split by C in two ways, and this has another neighbor, so that doublet would be split further in two ways, so you would have a doublet. If you zoom it, you will get this kind of thing, although it looks like a doublet here. The coupling constants are very small when they are vicinal, when they are geminal. Okay, when they are vicinal, their coupling constants are much higher. Okay, here is the depiction of that. These two are close in their dihedral angles, so they don't split each other that much, and these two are cis, these two are trans. Trans hydrogens couple in a stronger fashion or more intensely than the cis hydrogens, than the geminal dihydrogens. Okay, so if you take into account, if you look into the figures, the geminal coupling constant is very small, it's just tiny doublet kind of a thing, which in turn gets split by this hydrogen. But if this hydrogen is cis to each other, then you get about 6 to 10, and if it is trans, then you get about 11 to 18 hertz of coupling. So you can easily say the respective peaks corresponding to the cis hydrogen as well as the trans hydrogen by their chemical shifts as well as by their splitting pattern. Not only splitting pattern, but the extent of the coupling constants also will tell us some information about the structure of the molecule. Okay, this is how the tree diagram has to be developed. So in general, when two sets of adjacent protons are different from each other, the number of peaks in the NMR signal is given by n+1 plus m+1, right? In general, the value of J falls off with the distance, and it's dependent on the dihedral angle as well. J values have been tabulated for various alkenes, aromatic or aliphatic systems, so you can refer to them. But just to generalize, the geminal couplings are the smallest couplings that you see, and the cis couplings come next, and then the trans couplings. Something if it is trans alkene, so let's say these two are the isomers of the same alkene, we can tell them apart by looking at the coupling constants. If you have coupling constant between A and B, JAB as 5 to 10 hertz, then you can say that's cis related. If the coupling constants are higher, bigger, then you can call them as you can tell them apart as a trans isomer. Okay, so n+1 rule only holds good in certain cases, n+1 rule doesn't hold good in all the cases. Then you have to go into finer tree diagrams to draw them, and the total number of peaks in a given NMR signal is given by this rule, n+1 times m+1. 2 Okay, so if you practice some examples, it would be clear to you. Some of the common J values, as I said, are tabulated and they are given here. Trans, cis, axial to axial, axial to equatorial. Those can be equatorial to the axial, 1, 3, 1, 1, 2. All sorts of coupling constants are tabulated. There are computational programs where you can deduce the information as to how a given neighboring proton set is related to each other. Okay. A cyclopropane ring, again, these two are kind of coupling because some of them are cis or some of them are trans. Maybe they're running at a. This is not the case. You should have some substituent here. Then these are chemically not equivalent and they couple with each other. Okay. If this is just cyclopropene, then propane, then things would be much more simple. Okay. Anyhow, this is alkane in the ring. They can only have one orientation, that is cis orientation, so the couplings are much smaller compared to the trans couplings that we saw in other cases. This is epoxide. Depending upon whether it's trans epoxide or cis epoxide, the couplings would be different. Again, that's shown here. And ortho coupling would be different, para coupling would be different, meta coupling would be different, and that is given here, right? So for example, this is the hydrogen that is under consideration. This couples with this. This also couples with this. This also couples with this. But look at the intensity of the coupling. The coupling intensity is going down with the distance. This is 1 bond away. This is 2 bonds away. 3 bonds away. 3 bonds away is almost 0. That means it doesn't couple, right? In the aromatic ring, they are held in a fixed position. Probably they have residual coupling, small couplings. But in other cases, there are negligible splitting patterns with the distance. As I said, we can tell the isomers apart. This is the trans isomer, this is the cis isomer. The chemical shifts would be a little different, but even the J values would be different. By looking at the J values, we normally decide whether it's cis or trans, right? Okay, because the J values would be smaller if it is cis, J values would be bigger if it is trans. If all the, let's summarize what we learned so far. If all the hydrogens are equivalent chemically and magnetically, they don't split each other. Right. So for example, this is a dichlorobenzene. There is a symmetry, element of symmetry here, and this hydrogen is same as this one, and this hydrogen is same as this one. So there is one element, there is two-fold symmetry here, so you get only one singlet and it doesn't split. The moment you differentiate one of the halogens as iodine, so this is different than that, it's in turn different than this one. So you have two here, so there's only one plane of symmetry here, I guess. So you get two peaks, but this hydrogen is splitting the other peak, so you get a doublet for this hydrogen and you get a doublet for this hydrogen, and that's shown here. Okay. And if you have one more substituent, if you have alkyl substituents, not only you get this pattern, but also you get the peaks for these alkyl groups. Here we didn't have any alkyl groups, so we don't have any aliphatic range. We only have aromatic range. Okay. So let's take another case where we have a different situation. Here, this is the TMS peak. There is a doublet. This doublet is integrations. You can see how they are related. Looks like this is for 1 proton, this is for 2 protons, and this is for 6 protons, and this is for 1 proton. So depending upon the pattern, as I said, the typical patterns, you can say that there is an isopropyl group here because there is a doublet, there is a septet, right? The septet is because of these 6 neighbors, doublet of this methyls is because of this hydrogen, and these hydrogens do not couple with this methyl because they are 3 bonds away, so they cannot be counted as neighbors. Normally the hydroxy peak doesn't, hydroxy proton, the hydrogen attached to heteroatom, does not couple, but in this case it seems to be coupling with this CH2. As a result, this is a triplet. This CH2 itself has one neighbor here and one neighbor here, so that's a triplet here. Okay. In certain solvents, you can see the coupling of this hydrogen that is attached to heteroatom. In some cases, you don't see that, so you have to be careful when you have alcohols. Here is a case where you have 2 hydrogens which are attached to the same carbon, you would tend to think that they have the same chemical shift, so they should not be coupling with each other. But however, these hydrogens are diastereotopic because there is a chiral center here. If you were to have an absolute stereochemistry assigned to this, let's say if you had a beta methyl and alpha hydroxy, then you can assign some stereochemistry to that, and depending on that, this is either pro R or pro S. As a result, we have diastereotopic relation here between these two hydrogens. They couple with each other, so as a result of this hydrogen is a doublet, and vice versa, and so you see a doublet of a doublet for that, HA and HB, right? And the extent to which this hydrogen couples with that hydrogen is same as the extent to which B couples to A. So the coupling constants are reciprocal. And the aromatic protons couple to each other as well, but you need to have a powerful magnet to see this kind of splitting pattern in the aromatic region. If you have 60 megahertz, you just see a big multiplet here, or a big hump. When you have a higher magnetic field, you can see ortho splitting, ortho coupling, as well as meta coupling, and to some extent para coupling, right? So, and moreover, the integration is to 5 is to 2 is to 3. So that should tell you something about the substitution pattern of the aromatic. The moment if you have 5 hydrogens here integrating the ratio as is seen here, you should think of monosubstituted, right? So anyhow, the discussion should be here, though. The focus should be here. The diastereotopic hydrogens do couple with themselves, though they are attached to the same carbon. If there was not a chiral center here, then they wouldn't couple with each other. Let's say we had a methyl group here instead of hydroxy group, then these two would not be coming as a doublet of a doublet. They would come as a singlet. Okay. So any questions? If not, we'll just move forward and take some examples. And as I said, hydroxy proton sometimes does not couple with others, so it just comes as a singlet, as in this case. But in some cases, some solvents do limit the hydrogen bonding, and as in then that does show up. So depending upon the solvent, depending upon the concentration, for now we can probably safely say the hydrogens that are attached to heteroatoms need to be taken carefully. Okay. If they exchange rapidly, they don't couple with the neighboring CH2. If they don't exchange rapidly, then they do couple. This exchange is dependent on the concentration and the solvent that you normally use. Okay, I'm going to skip this one because this is the hydrogen bonding. See, this is an ethanol. If it is in water, it would exchange quickly. If this is not a hydrogen bonding solvent, then exchange would not be as faster. Then it would be like intermolecular hydrogen bonding between two ethanol molecules, and that is dependent on concentration. As a result, you would not only see the differences in the chemical splitting patterns, splitting patterns, but also you see the difference in the chemical shifts depending upon the extent of the hydrogen bonding. For example, we'll see that in a minute. Okay, there is another test that one can do to find out the extent of mobility of this hydrogen, or the rate of exchange of this hydrogen, by doing a deuterium test. If there is any exchangeable hydrogen in your molecule, just take in D2O, shake it for a minute or two, and then go to NMR room and place your tube in the NMR machine and look for the signal after and before the NMR. This is called D2O exchange, right? D2O shake. So this was taken before adding the D2O. Then you added few drops of D2O and shook it for a while. The oxygen, the hydrogen that is attached to oxygen, has been exchanged to the deuterium, and in this window we don't see deuterium. In the window there we are focusing on hydrogens. That frequency is different than where the deuterium resonates, so we don't see the deuterium peak here, and we only see ethyl peak. That tells us that there is one exchangeable hydrogen in our molecule. Okay, this deuterium exchange experiments are useful when you have exchangeable protons such as acids, alcohols, amines, and so on and so forth, that are attached to heteroatoms. Anyhow, to summarize, The protons that produce signals on the right side of the NMR have higher amount of valence electron shielding. We already talked about this. So the chemical shifts depend upon the hybridization, electromagnetic electronegativities of the atoms, and as well as anisotropic effects that are produced by the ring currents. So those things you should remember. The protons that resonate and towards zero experience less magnetic field, okay, than the protons that are deshielded. So don't go by this one, okay. This is where if you have a constant frequency, now this is in the old NMR case where we had field as a variable. Now we have radio frequency, radio waves as variable. We keep the field as constant. Anyhow, I'm going to skip some of the slides. So once you know all those four parameters that we talked about, the number of peaks, the positions of the peaks, and integration of the peaks, and the spin splitting of the peaks, you can analyze. You can start analyzing the spectrums. Spectra. And you have to play a detective. The hydrogen NMR alone is not going to help you. You have to rather choose from all the spectroscopic tools. We'll be talking about C13. We already talked about IR and mass and UV spectroscopy. So you take the help of all these spectroscopic tools and collect the tools from as much as you can collect, and then eliminate the suspects as you would eliminate in the forensic science, right? You have to be careful though. You have to double check, cross check, confirm, and then assign the structure. So with that, we'll stop these discussions here, and then we'll continue in the next class as to how to use the proton NMR spectroscopy to determine the structures. Okay, thank you.